Welcome you all for this second session of sinusoidal steady state analysis. I am Dr. S.B.MOHAN. Today I am here to give you a short note on sinusoidal steady state analysis as a part of CATE coaching sponsored by S.A.E. Engineering College, Department of ECE. So the last session we discussed about RLC series circuit, RLC series circuit for AC responses, and of course combination of parallel also, where we had discussed about this different types of powers, where you got average power, resultant power, reactance power, and of course apparent power too. Apart from that, we discussed about the power factors, where you got unity power factor, lagging power factor, and leading power factor. Today, let us discuss the next part of the sinusoidal steady state analysis, where we'll be having a note on resonance circuit. So generally, when we talk about this sinusoidal steady state analysis, we require to know when the circuit will become, when the circuit will act for maximum responses. So when we talk about the responses, we clearly know that current flow will be the maximum response. And of course, the power consumed by the circuit will be the response. So, when we consider the resonance condition, we got certain points where the current flow will be maximum, and of course, the proportionate power also will be maximum. Right. So starting with that, let us start with series resonance circuit. So this is your RLC series circuit, where a sinusoidal response has been given, input has been given, which will be say stated that V of t. So here I will specify it as VT, VM. Actually, it is V of t. So V of t is equal to. Let me put it here. So we can write this as V of t. V of t is equal to Vm sine omega t. Okay, Vm sine omega t. Right. So here, this Vm is the magnitude which will be acting in the circuit. Okay, so because of this maximum voltage, you'll be getting some responses. Now, when this Vm is connected to this RLC series circuit, let me put this here. Okay, so you'll be getting a current flow since it is a closed circuit. It is well known that for a closed circuit, the current flow will be available. So this is what the closed circuit of RLC series, where the current flow I will be available. Current flow I will be available. So this current flow will become maximum at one particular point. So what is that? So it is well known to us that impedance is nothing but R plus JX. Okay, which is nothing but the resultant value of resistance and reactance. X is nothing but the reactance value. And of course, here this X, will be equal to XL minus XC. XL minus XC, where XL is nothing but inductive reactance and XC is nothing but capacitive reactance, which is known to us. So now this impedance value, will be inferred in this circuit, and of course, resistance is a component which is independent of frequency, but the reactance is depending upon frequency. So since it is the sinusoidal response, so frequency will be taking part, where omega is nothing but the frequency. Actually, it is called as angular frequency, which is equal to 2 pi f. So therefore, your frequency will be taking part in the circuit. So this frequency, we'll have some modifications, or will be creating some modifications in the current flow because of the variations in inductive reactance as well as the capacitive reactance. So XL is nothing but 2 pi FL, and of course XC is nothing but 1 by 2 pi FC. So when the frequency is increasing, so let us take that the initial frequency, let us see this characteristic curve. Okay, so this, let me come this side so that it will be visible. So here, this is your frequency response of RLC series circuit. So where this is the starting point of your frequency. So when the frequency is slowly, gradually increasing, so what happens now? The current flow will be gradually increasing. The reason for this is for F is equal to say 0. Your XL will be equal to 0, and of course XC will be equal to infinity, which means that XC will be very high, and of course this part of the circuit will become open circuit, and therefore the current flow will be 0. Okay, but XL will obviously it is equal to 0 because XL is directly proportional to frequency, X is indirectly, inversely proportional to frequency. So when the current slowly increases, okay, when the frequency is slowly increasing, this XL will be gradually increasing and the XC will be gradually reducing. So what happens in the sense the current, the XL value will be gradually increasing. So simultaneously, the current flow also will be gradually increasing because of the reduction in XC. Okay, so we know that XL minus XC is available in the impedance part. So therefore, this infinity will be getting reduced and this XL will be gradually increasing. So what will happen now? The current flow will be gradually increasing. So at one particular point, okay, the current flow will be reaching its maximum. At this place, your XL and the XC will be equal. So this is the place where the resonance condition occurs. The resonance condition will be obtained in our from the circuit. So therefore, the condition for RLC series circuit to be under resonance is XL is equal to XC. So at this place, the current flow, this is your current value. So this is your current. So the current flow will be maximum at this XL is equal to XC, and respectively, you'll be getting a frequency for this particular, and that frequency is called as a resonance frequency. In some references, you'll be having F naught as, what is that resonance frequency? In some references, you'll be having FR as the resonance frequency. Later on, what happens in the sense, when you further increase the frequency after this resonance condition, okay, the XL value will be gradually increasing again, XC will be gradually reducing. So after this, the current starts to reduce because here the capacitance will be dominating. Capacitance will be dominating. Here, this side, the inductance will be dominating. Inductance will be dominating. So here, the inductive reactance will be gradually increasing. Because of that reason, the current flow will be reducing for further increase in frequency. So when your frequency is very high, okay, we can state that the inductive reactance will be very high, and of course, the capacitive reactance will be minimal. Okay, so that is what this response will be inferring. We can infer from this response. Now, when the current flow is maximum, at this place, the power also will be maximum. So we'll be getting maximum power. So therefore, this is the place where we'll be having the current as maximum as well as the power as maximum. Now, when we talk about the voltage across resistance, inductance, and capacitance, okay, so here we know that V is equal to IR by Ohm's law. Okay, so here I into R will be the voltage, and of course here it will be I into XL, and here it will be I into XC. Okay, so these are the voltages across the different components. Based upon the frequency, the current value will be changing, or because the voltage across every component will be changing. So that is what these equations are supporting us. So when we talk about the total current flow, when you talk about the total current flow, we'll be getting voltage divided by impedance. Here the voltage is Vm. Okay, so we are talking about the magnitude alone. So the voltage is Vm, and the reactance value will be impedance value will be R plus J omega L plus 1 by J omega C. If it is in the numerator, we can state minus J omega C. Okay, since it is the denominator, we are specifying it as 1 divided by J omega C. So here, this J component, when it comes to the top, numerator, this will become minus. So that is the reason. So this is what your current equation is. Okay, so therefore, here Im is the magnitude of the current of I, and theta is nothing but the angle made. So this theta will decide the power factor. So when you see in this response, okay, so here when the capacitance is dominating, okay, we can state that the power factor will be leading power factor. Okay, and of course, when the inductance is dominating, you'll be getting the lagging power factor. At resonance, the power factor will be unity. We know that power factor is nothing but cos pi. Okay, so therefore, which is nothing but R divided by Z. R divided by Z, where R is nothing but the real component, Z is nothing but the resultant component, which has been obtained from the power triangle. Okay, that is what. So here we can calculate the value of theta by using this formula. Okay, which is nothing but tan inverse of X divided by R. Tan inverse of X divided by R. So X is nothing but omega minus 1 by omega C, and of course R is nothing but, as usual, resistance value. So this is how that value of theta has been, or you can say will be calculated, right? So next is Right. So now, as we discussed, I told you that the resonance condition for an RLC series circuit is XL is equal to XC, and the resonant frequency. Okay, and the resonant frequency. Yeah. So the resonant frequency is FR is equal to 1 by 2 pi root of LC. This will be obtained from this part where omega L is equal to 1 by omega C. So replace 2 pi FL, which is equal to 1 by 2 pi FC. And of course, from this you'll be getting, if you solve for frequency, you'll be getting 1 by 2 pi root of LC. And of course, under resonance condition, the value of impedance, we can say the impedance value will be equal to resistance, and this will be confirming that the power factor is unity under resonance condition. And of course, the current at the resonance value will be I is equal to E by R. So here E is nothing but voltage. Some references will be having V. Okay. And of course, I told you that power is nothing but I square R. Or we can write this as E square by R also. Okay. Under resonance condition, I mean. Okay. Next, when we talk about that other parameters which can be inferred from this resonance condition will be bandwidth. So bandwidth is nothing but the difference between the upper cutoff and the lower cutoff frequency, where F2 is nothing but the upper cutoff and F1 is nothing but the lower cutoff frequency. So therefore, these cutoff frequencies F2 and F1 will fetch as a power called as half power. Will be fetching us the power called as half power. Okay, so FR or F0, resonant frequency will be fetching as the maximum power. Okay, and this F1 and F2 will be fetching us the half the maximum power. Okay, so therefore we can call this F2 and F1 as half power frequency too. Right? So from the bandwidth we can calculate the quality factor. So the quality factor is given by FR divided by F2 minus F1, where F4 is nothing but the resonant frequency, and F2 minus F1 is nothing but the bandwidth. Okay, so when your FR is very, high, okay, we can state that the quality factor will be increasing. Okay, and of course, if your F2 minus F1, if your bandwidth is lower, the quality factor will be increasing. If your bandwidth is wider, or can say higher, okay, we can set the quality factor will be very low. So this ratio will be fetching us for designing of filters. So that is apart from this. Okay, so we'll come back to the quality factor again. The quality factor can also be obtained by using this formula. Q is equal to 1 by R root of L by C. So this has been obtained by substituting the value of FR is equal to 1 by 2 pi root LC in this formula. From this you can obtain this. And of course, the same Q value can be obtained by 1 divided by omega naught CR, and of course, omega naught L by R. So therefore, you got three different formulas. And of course, apart from that, 2 pi F naught L by R. This is another formula. So therefore, you can use either of the formulas depending upon the given parameters to calculate the quality factor. The quality factor will decide the circuit's performance, quality of the circuit. Okay. And of course, as we discussed, the current flow remains maximum for a series RLC circuit under resonance condition. Next is, what about the voltage? We are talking about the current alone, and of course the frequency, different parameters, quality factor, as well as the bandwidth. So now when we talk about the voltage, so here, when we talk about the voltage, okay, you'll be getting a maximum voltage across the inductor and capacitor, okay, during this frequency. So omega is equal to omega naught root of 1 minus 1 by 2 q square. That Q is nothing but the quality factor. EC max will be known as maximum voltage across a capacitor. Okay, as I told you before, some references will be having V as parameter. Voltage parameter. Some references will be having V as parameter. So here taken as E. Likewise, for about inductance, EL max. I'm sorry. For inductance, it is omega is equal to omega naught divided by root of 1 minus 1 by 2 q square. So these are the formulas for maximum voltages. And as I told you, we will be having half power frequency. The half power frequency will be obtained from the upper cutoff as well as lower cutoff. And of course, the condition for half power frequency will be making the difference of, okay, so the reactance and resistance will be equal. Okay, so when the resistance and reactances are equal, okay, you'll be getting the half power frequency. frequency. Okay, so at how power frequency, what would be the power factor? When under resonance, the power factor will be unity. Okay, and of course, the power will also be maximum. But when we talk about the say how power frequency, the power factor will be 0.707. Power factor will be 0.707. So these things you have to keep in mind. So this ends about your RLC series circuit. Let us talk about parallel circuit. So this is the parallel combination. Okay. And of course, for this, the resultant current is given by VR divided by L by CR, which will be fetching as VR by ZL square. ZL square. Okay. So this is about your resultant current in your RLC circuit. And of course, the voltage remains constant for all the circuit, all the components. Elements, I mean. Okay, so when you talk about the Q factor, it is 2 pi FRL by R. It remains same for similar to that of your RLC series circuit. And of course, the quality factor, the resonant condition, resonant frequency also will be the same. FR will be equal to 1 by 2 pi root of LC. And the condition for resonance also will be equal to, will be the same. XL is equal to XC. Okay, actually, we'll be writing here it as in terms of admittance. We'll be writing in terms of admittance. So that will be easy for us to calculate. So we'll be writing YL is equal to YC. So YL is nothing but 1 by XL. YC is nothing but XC. So if you reciprocate this, you'll be getting the same. Okay, actually you're right in terms of you're right in terms of what is that? I'm sorry, here it is not right. Let me erase it. Okay, this is wrong. Actually, this 1 by XL is equal to 1 by XC. Okay, so this is about your condition for resonance where OL is equal to YC, admittance in terms of, when you talk about reactance, it will be XL is equal to XC. Right? So next is when we talk about the impedance effort, the impedance effort for this circuit will be given by L divided by CR. L divided by CR. Okay, the impedance is dynamic impedance and it will be maximum under resonance. The impedance will be maximum. Okay, impedance will be maximum. For series circuit, the impedance will not be maximum. Impedance will be equal to resistance value, which will be negating the reactances. Okay, so that is what here. So next is, since the RLC parallel circuit draws minimum current under the resonance, it is called as a rejector circuit. It is called as rejector circuit. Okay, since and of course this parallel combination will be fetching as some sort of tuned circuits. Okay, so this is the base for creating a tuned circuit. Okay, which will be available in the which will be studied in electronic side. Okay. So for tuned circuits, this RLC parallel circuit will be supporting. Okay. So otherwise, the combinations of RLC parallel and series will be having more or less equal conditions in terms of resonance, and of course the power factor, quality factor will be the same. Okay, bandwidth also remains the same formula, F2 minus F1. Okay, so there are some minute variations where if you calculate the bandwidth, okay, you'll be getting R by 2 pi L in the case of series circuit, and for parallel circuit, you have to just reciprocate it. That's all, nothing else. Okay, you can write the, what is that, bandwidth or quality factor in terms of resistance, inductance, and capacitance. Okay, put together. And of course, this is a comparison. You got different parameters here. So impedance and resonance will be minimum, and here in the case of parallel circuit will be maximum. When you talk about the current flow will be maximum, the current flow will be minimum. Okay, I forgot to tell about the response of your what is that response of parallel circuit. So the parallel circuit will be like this. The response of the parallel circuit will be, so let us take this as our frequency. So this is how your response will be there. So that this is your current, and this is your frequency. So this is your minimum current. Right. So when your F is less than FR, what does you have? F is nothing but the supply frequency, FR is nothing but the resonant frequency. When F is less than FR, okay, the series circuit will be having dominance of capacitance. Therefore, the power factor will be lagging power factor. Power factor will be lagging power factor. When your F is greater than FR, okay, you'll be having what is that? So here it is leading power factor. Okay, in the case of capacitance, in the case of inductance, it will be lagging power factor. Okay, just opposite to that of this. Here we'll be having lagging power factor. Here we'll be adding leading power factor. So here this is your lagging power factor, and here it is leading power factor. And when your circuit is under resonance, the power factor will be unity in both the cases. It will be unity in both the cases. Okay, and as I told you before, you can write this value of Q factor in terms of XL. So here it is XL by R. Similarly, there also it is XL by R. Okay, so now we can state that the resonance circuit will be called as a magnifier circuit. Okay, for series circuit, the voltage will be say magnified. Okay, and of course, for parallel circuit, the current will be making it as a magnified circuit. So this is about your resonance conditions and resonance circuit. Okay, let us work with some simple problems. Okay, so an inductor having a Q factor of 60 is connected in series with the capacitor having a Q factor of 240. Okay, the overall Q factor of the circuit is so they have given the Q factor in different conditions. Okay, so when the inductor having a Q factor, capacitor is having a Q factor, okay, you have to calculate the say overall Q factor. So this is the formula to calculate the overall Q factor, where you need to just substitute the values of Q factors, and then we have to solve it. Okay, just a minute here. Yeah, so we can get it now. So here QLS is given in the problem as 60. So 60 into 240 divided by 60 plus 240. Direct substitution, if you get, you will be getting the answer as 48. Now, the next problem is voltage and current across a load are as follows. Okay, so here V of t is given, I of t is given. This is the voltage and this is the current. Okay, so now we have to find the average power. So we know that average power is given by VI cos phi. This is the average power formula. This V is nothing but VRMS, I is nothing but IRMS. V is nothing but VRMS, I is nothing but IRMS. And of course, cos phi is nothing but the power factor value. For cos phi is nothing but the power factor value. So here they have given the voltage as V of t, I of t as the current. So here this is your VM and this is your IM. Okay. So actually for calculating the power factor value, it will be VM by root 2. Calculating the power value, VM by root 2, IM by root 2, and power factor, it is nothing but cos of phi. Phi is nothing but 60 degrees. Substitute there, the resultant value will be 250. The result of this problem will be 250 watts. Okay, just substitute and get it. What you have to do is 100 divided by root 2, then 10 divided by root 2, cos into 60. Okay, so you'll be getting 240 watts as the solution for this problem. Right. Next is, so the total power dissipated. Let us go to this problem a little bit later. Next question is, if the capacitor in RLC circuit decreases, the resonant frequency increases. Okay, if the capacitor in RLC series circuit decreases, okay, the resonant frequency increases. Obviously, it is going to be true. So how it is so? As I told you before, okay, when the frequencies keep on increasing, the capacitance will be getting reduced. Capacitor reactance will be getting reduced. So therefore, this statement is going to be a true statement. Next, a certain series resonance circuit has a bandwidth of 2 kilohertz. If the existing coil is replaced with one having a higher value of Q, the bandwidth will reduce. The bandwidth will decrease. Okay. So when the resonance circuit, okay, when the resonance circuit has a bandwidth of 2 kilohertz, okay, if the existing coil is replaced with one having higher value of Q, if the Q value is increasing, obviously the bandwidth will be reducing. Okay, we know that Q is equal to FR by bandwidth. So if the bandwidth is increasing, Q value will be reducing. Okay, so therefore the answer for this is decrease. The answer for this is decrease. Now coming to this problem, it's a good problem here. This has appeared twice in this model has appeared. Okay, so let me work out this. Here they have given an AC source. Okay, and of course they are given some combination of components in say both series as well as in parallel. Now our objective is to calculate the value of XL and R. How to calculate this? They have given the total power. Total power is 1 kilowatts. Total power is 1 kilowatts. We have to calculate the value of XL and XL and R. Now, when the total power is given, okay, we can calculate the value of voltage. So here we can say power is equal to VI cos phi. VI cos phi. Okay, so here V we do not know, I it has been given as 10, cos phi we do not know. Okay, so how to get this solution? How to get this solution? So what we have to do is, okay, from the power divided by current gives you total voltage applied. Power divided by current gives you total voltage applied. And of course, here 10 is the total current. The current will be the same in this place also. So therefore, from this we can calculate the value of R as well as EH. Now, actually, when we talk about the total power consumption, generally we know that the power consumption will be only in resistance. So you got two resistance. Okay, so let us take the resistance I square R as a formula for power consumption. Okay, so therefore let us take this as R1 and this as R. So I square R plus I square R2. Okay, this will be equal to 1 kilowatts, which is nothing but 1000. I square R1 plus I square R2. R2 is nothing but the value of R which you have to calculate. So I is given in the problem. So therefore 10 square into R1 is nothing but 1 plus 10 square into R, which is equal to 1000. So if we solve this, you'll be getting the value of R. If you solve this, you'll be getting the value of R. Next is we have to calculate the value of XL. So to calculate the value of XL, we need to know what is the say voltage across on this slide. So the voltage across here is 2200. So with this voltage, we can calculate the value of XL also. Okay, because we will be giving you total Z. If you find the Z, let me write it here. Okay, so here voltage is V divided by I will be giving us Z. So which is nothing but 200 divided by 10 give you Z. Okay, so this will nothing but will be equal to 20. Okay, so 20 will be the total impedance. So impedance is equal to R square plus XL square the whole root. Okay, so R is obtained from this problem. XL we can solve this. So therefore XL square is equal to ZL square minus R square. Okay, so R is calculated. Okay, so therefore from this you can calculate the value of XL, which is nothing but root of ZL square minus RL square. Okay, so this is how we can calculate the value of XL. So this is about your second part of sinusoidal analysis. Hope that you would have enjoyed the session. Thank you.